Okay, very good. So today we're happy to have our very own Anthony Pullen. I think you all know him, but just a brief introduction. So you did your PhD at Caltech, finishing in 2011, and then postdocs at Caltech and Carnegie Mellon, and came here to NYU in 2016. So Anthony is the science lead on EXCLAIM, which is an intensity mapping survey that I guess will be a big part of this talk. And you're also a member of DESI, funded by NASA. And yeah, so we're really excited to hear you talk. So thank you, Anthony.
Thank you, Matt. First of all, thank you all for being here. I'm excited to talk today about much of my work, not all of my work, but much of my work, specifically thinking about how best to probe galaxy physics using line intensity mapping. So basically, we're going to talk about how line intensity mapping is a very exciting field. It's a new observable to be able to probe both cosmology as well as physics of galaxies. But one thing that's important is to project how basically the line intensity map will be affected by varying properties of galaxies, which we may want to probe and may also be important for teasing out cosmological signatures as well. And so that's what I'll be talking about today, how my research group is pioneering that effort. So this is work that I've done in collaboration. Well, first of all, of course, we wouldn't be here without the physics department and the Center for Cosmology and Particle Physics. So I'm just glad to be a part of this group, and it's been a great time over the past 6 years of being part of this family, and it's been very helpful for my research. So this work has been done in collaboration with basically folks at the Goddard Space Flight Center, as well as the Center for Computational Astrophysics at Flatiron, and in addition, I also have a collaborator at the Carnegie Observatories. I also want to just acknowledge just others who have also been supportive as well. So much of this research is funded by grants from both NASA as well as the National Science Foundation. Also my work is supported as well as in a visiting scholar position at the CCA. And then finally, of course, I want to acknowledge my research group, which includes students and postdocs that were formerly in my group and have now all gone on to do better things, between postdocs and grad school and industry jobs, and as well as my current set of current students, as well as Patrick Tracy, who's not my postdoc, but who's affiliated with me, and we do a lot of work together. So I just want to acknowledge all these people as well. Okay, so this is the outline of my talk. So first, I'll give a brief overview of line intensity mapping, why it's important, and basically a hint to the question that I want to answer. Then I'll talk about line intensity mapping simulations and how we constructed these in order to help in order to move forward the field. I'll also talk about some recent work that we've been doing to construct an inference, a line intensity mapping inference model for galaxy properties that will be very useful to really be able to make precise constraints of galaxy physics from large scale structure, and may also be important for cosmology. After this, I'll hopefully, if I soon have time, I'll give an overview of my work with the EXCLAIM survey, the EXCLAIM Balloon survey, and what in the science we will learn from that mission, as well as some cosmology work related to line intensity mapping that my group has also moved forward. So this is sort of a map of the cosmic dawn. So 300,000 years after the Big Bang, atoms began to form, leftover radiation became the cosmic microwave background. But you had basically this the universe filled with hydrogen and helium in an epoch in which star formation didn't exist, and so you call this epoch the Dark Ages. However, about 400 million years after the Big Bang, the galaxies and stars were able to form, and this is the period we call the cosmic dawn. Those stars were radiating in ultraviolet, causing the universe to go, intergalactic meteor go from a neutral state to an ionized state. We call this the epoch of reionization. And then finally, as matter begins to cluster more, we can begin to form not only galaxies, but also groups of galaxies called galaxy clusters. and this begins to form into the large scale structure we see today. We also, of course, have cosmic expansion. Sorry, not only cosmic expansion, we have cosmic acceleration of expansion, which we believe is the evidence of dark energy. But others disagree. So, but looking at galaxies are basically the corner of the realm. It's what we use in order to be able to measure large scale structure post CMB, post cosmic microwave background, but which is very important for the work we do and in order to understand cosmology. But the big problem is that you do have a lot of missing galaxies. By this image constructed by Patrick actually a long time ago, we see here a simulation of a telescope, the Very Large Array, where the red dots represent the galaxies that would be observed by sort of this big, huge dish, the biggest that we have, really, at least on the ground. Well, ever really, because you can't put it in space. And then, and it was where the gray dots actually represent all the galaxies that really be there, but they're just too faint in order to be able to detect. And so those red dots are all you would have, and we can do a lot with those bright galaxies to constrain large scale structure, but there's more we could do if we had access to the full structure. And however, it turns out that here is a simulation of what microwave emission from those galaxies could look like. And this would be, and the question is, and the thing is that if we had access to all the information in this pattern here on the right, we could do more cosmology and possibly even probe much earlier times than we can with just the red dots. And so the question is, how do we access that information? So line intensity mapping is a way we can access that information. So if you see the picture on the top, it sort of gives you an idea of what you could possibly do with line maps. The idea being that each of those slices represents a slice of large scale structure that you can map using an emission map, where you take which receives all the emission from all the galaxies onto your map. And so it allows you to probe much fainter galaxies. It allows you to probe galaxies that are much farther than you'd be able to detect with a galaxy survey. And so you can use that in order to map, and you see potentially use that to map large scale structure. This is what, in an ideal scenario, this is the image on the right is what a line intensity map would look like, where sort of the part on the left is what you would see on the sky, but on the part
what frequencies are we talking about?
So it depends on the instrument. Much of the work now is either in the radio. That's where you're looking at, for example, if you want to look for 21 centimeter emission from H1, from neutral hydrogen, or in sort of the infrared.
Because this thing does not look like optical, obviously, right?
No, that's right. This is not what you would see with your eye. This is in the microwave range. Yeah. So whereas the image on the right is sort of, you see the little slices, and these represent basically the slice, basically looking along the line of sight, and each of those maps will represent a different time period as you're looking back in time. So the key is that, oh yes, it's Mark.
So this is my really just dumbness, but the scale bar on the bottom is microkelvin.
That's right.
And what's
yes, that's microkelvin.
And what's the temperature of the microwave background?
So the temperature of the microwave background is 2.7 Kelvin, or at least locally.
So like, why would you what does the microkelvin mean then? Shouldn't everything be at least 2.7?
So this is with any CMB contribution subtracted. Basically, what you want to look at is you would have a mean signal, and then you have small perturbations on top of it. And so you would, well, one way is you would try to subtract the mean signal. A better way is to actually acknowledge that that's there. But if you use Fourier transforms, you can actually see, you will have your signal at sort of k equals 0, which will be your mean signal, and then the other scales for higher k's in your Fourier transform you would get the sources from the fluctuation.
And there's like this structure in the cosmic microwave background, right? So like,
Yes.
this is evidence of inflation or something, right?
Mhm.
And the scale of those fluctuations is microkelvin also.
So those are order of 10 to the -5. So yeah, it's an order. Yeah, those are order. Yeah, so those are an order of tens of microkelvin as well. So
And so-
these are even smaller.
Those are also subtracted off in this image.
Well, so you wouldn't want to subtract it. There's more intelligent ways to do it, where you can sort of fit but particularly because that's a continuum signal, so you'd probably want to just you would construct your estimator such that you can subtract off the smooth part, usually using a polynomial in order to remove the smooth part in order to minimize, because it wouldn't bias your signal, but if you want to minimize noise, you do want to remove it. So
basically what you're saying is those fluctuations are still large on the scale of what you're looking at here.
Yeah.
And so the microwave background is taken care of. I shouldn't worry about it.
yeah.
They are larger or they occur on different length scale?
So the perturbations from the C and B is still larger, but so the perturbations on the C and B are still larger. But one thing is, but that would just be an additional signal, and it's not just the C and B. There will be other signals like the microwave signal, the Milky Way, for example, will also emit these frequencies. One important thing you can do is with many of these signals, there are continuums, so you can try to subtract them out that way. But even without doing that, one tool that we use often is using something called cross correlation, where if you cross correlate the intensity mapping signal with either a galaxy survey where you have maps of galaxies or another intensity mapping survey, if you cross correlate those, anything that's not correlated should cancel out. And so one thing you would expect, right, is that the Milky Way should not, the pattern of image of intensity from the Milky Way should not correlate with large scale structure, from eons. So you can construct things like cross correlations that allows the signal to fall away.
I see. So there is a whole industry of how to extract this part that
Yes.
you are looking at from many others, which are also interesting.
Yes, well, we have to always consider this too. We're going to consider this in EXCLAIM. That's not what I'm going to be focused on today, though, just to be clear. But yeah, that's a whole, like you said, there's a whole industry that's focused on.
Sorry, just while you're stopped. Like, I'm not supposed to understand that top left thing, right? Because it's I can't read anything on it. So
Yeah, just so you know, so the x-axis is frequency in gigahertz. The y-axis is so this is a square, basically a degree by degree size. It's a sampling of a degree by degree patch that you can see. This is a representation.
And in the upper left and the upper right, the other left, the upper right, the frequency scan is integrated over X. Is that right?
So
Or
no,
is
it's
it
not
slight?
integrated over X. It's in it. Well, okay, so there is no X on the X. There is no position on what the horizontal axis. That's frequency.
Absolutely.
And that can actually come from many different positions along the line of sight, coming from different lines. The good thing though is that those parts should not be correlated, so you can use cross correlations in order to.
But again, just looking at it, it looks like it's sort of a flattened out version of the figure, and that's plotted in X and Y. Like I can see, I was just trying to understand where the features in the XY plot show up in the frequency plot, and it looks like the frequency plot is integrated over.
Yeah, there will be patterns of perturbations along the line of sight, and that's what this represents. That's what this represents. Yeah. Then this is a simulation, by the way, for just one line, so you can map it directly with position, but in reality, you would have many contributions to this.
So line here is a line of sight. Yes, or a frequency line.
Yeah, so the frequency will represent the line of sight for one line, and then if you have many lines, all those can contribute in different ranges of frequency. But again, we have the tools to extract.
Anthony, you mentioned 21 centimeter emission. What's the redshift range that you can look at that in?
Well, in principle, based on physics, people think that 200 is like the maximum, but we're not going to get there for many decades probably. But right now, current measurements, so Hera is the most advanced experiment right now that wants to look at high redshifts, and that is, I believe it's up to I think it's up to redshift 15. Well, no, actually redshift 20 that it hopes to be able to map.
Okay. So meters. Yeah. Okay.
Yeah. Of course, if you if you try to do anything in space, and then you got to put it on the moon, because you need really big. You need to basically be able to build something on Earth in space, so it can't be in orbit. So it has to be. But anyway, so because intensity mapping can map much larger volumes in galaxy surveys, it's great for appropriate cosmology where activity happens on very large scales, as well as gravitation. Again, if you want to test gravity on cosmological scales, since gravity is pretty well constrained on solar systems today. And then of course, because you're mapping many lines, because you can map the emission that comes from many lines, this would be great for galaxy evolution, which will affect which lines are emitted and their intensities at different events. So if we're going to talk about non-intensity mapping, we got to talk about the statistics. So the main statistic that's used is something called the power spectrum, which is just a statistic that describes how perturbations are correlated along length scales. So this is what a power spectrum looks like in the top right corner, where basically this tells you the strength of perturbations how two perturbations that are located at a certain distance apart from each other are correlated. So larger correlations on larger scales are mapped on the left-hand side, correlations on smaller scales are mapped on the right-hand side. And these, measuring the power spectrum, it's really sensitive to the mean and variance of intensity perturbations. It's not actually sensitive to other orders of the sort of the distribution of intensity fluctuations. The voxel intensity distribution, which is sort of a 1-point PDF measurement of intensity, intensity maps, is something that can actually it can actually probe the full distribution of intensities, which has information in it, and this is something that Patrick Bracey has been a pioneer in. And of course, I mentioned the cross power, and then of course the cross power spectrum is a way that I mentioned earlier that you can use to, in order to remove effects from both interlopers as well as forelines. So measurements have been done. We're still building the pathfinders, but we have been able to use instruments that were originally built to measure the cosmographic background and repurpose them to measure intensities of average intensities of lines. So this is a plot from work that was done by my student, former student Sheng-Chi Yang, who's now a postdoc at Carnegie Observatories, where we actually made a detection of excess intensity in the Planck intensity maps, cross-correlated with quasars from the Sloan Digital Sky Survey. And we found this, and we were able to make this constraint. And these lines here are just other models predicting what the intensity of ionized carbon, or C2, would be in those models. And this is how our measurement compares to those models. I also show here two other measurements that were done by others in the community. One by Rupert Croft at Carnegie Mellon, who measured the power spectrum from Lyman alpha emission, cross-correlated with quasars, and another from Garrett Keating, who's a scientist at CFA and Center for Astronomy at Harvard. And so that one, he measured emission from carbon monoxide and used that in order to constrain molecular hydrogen, which carbon monoxide is a tracer. So here is sort of a chart that describes basically what line intensity mapping inference would be and what we want to do. So the blue squares represent data. So we want to take line intensity maps and convert those into useful statistics that we can use. And then the green represents theoretical models. So you can, if you have a model of how cosmology would clustering of matter, and a model, as well as how that turns into galaxies. So like we'll let bias clustering, we'll let the non-linear clustering in the spherical collapse, we'll let that all live in the cosmology model. And then this square represents galaxy evolution emission model, which represents how galaxies emit, what their luminosities are in different signatures depending on the properties of those galaxies. So if you have maps with some intelligent idea of statistics, galaxy evolution model, emission model, and the cosmology clustering model, you should put these two together in order to get the statistics model that you can then combine with your statistics data with some kind of MCMC or Monte-Carlo Markov chain or some intelligent method in order to be able to understand, in order to be able to probe galaxy evolution and cosmology. This stuff at the top, the data, there's much innovative work that's going on. In addition to, of course, the volatility distribution I mentioned earlier. But there's also the statistics, of course, there's machine learning that you can also try to use to take the chart maps directly in the embedding, but I won't talk about that in this talk. There's also cosmology, which is basically subtle work to first order. Many people over 2 decades have really worked this out to first order. There's much work that still needs to be done as far as predicting nonlinear clustering, clustering on small scales, but those are effects. Basically, intensity mapping is probably not going to be able to really probe that for another decade anyway. So we can just leave that to the side, and this is pretty much done for us. The thing though that is not really done is making a galaxy evolution emission model. This is very underdeveloped. If the models that we currently use could lead to biases in measurements, and so this is really something that I wanted to work on. That's what my talk will mostly be about. So, in order to talk about non-intensity mapping emission, we need to talk about dark matter halos. So, galaxy emission. This is what sources the line intensity maps. For the most part, there are other sources, of course, like the intergalactic medium. You can get 21% emission and laminar emission from that, but really the bulk of the emission, particularly in epochs after reionization, so about the last 10 billion years, that's 6 billion years. That comes from mostly comes from galaxies. Galaxies though cluster in dark matter halos. So what is a dark matter halo? So a dark matter halo is a sphere of dark matter. Our current understanding of large scale structure is that basically all of the dark matter exists in spheres of dark matter that we call dark matter halos. And again, these tend to develop in regions. They tend to grow in regions where the overall matter density is much higher than on average. And there's a prediction based on large scale structure models of how dense that needs to be. And then galaxies themselves then form in the vicinity of dark matter halos. So then we can also describe what we call a halo luminosity, where it's the luminosity of a halo is obviously dark matter doesn't shine, but the luminosity of a halo, we consider that as the luminosity of all the galaxies that are associated with that halo, such that then halo luminosity, and then those halo luminosities can be modeled as just a sum. It's just a sum of the luminosities of the individual galaxies associated with that halo, which usually consists of a central galaxy as well as possibly a few satellite galaxies. This is, for example, a cluster simulation of the cluster around the Milky Way, with us being at the center, and then you have some satellite galaxies around the Milky Way. And then finally, those halo luminosities can then be modeled as functions of the mass of the halo and its redshift, which describes which is based on cosmic expansion. It actually describes how far away that halo is. The idea being that if a more massive halo will tend to create more galaxies as well, and also to depend on the epoch in which that halo was formed can also influence the galaxy dynamics.
And the connection between the halo luminosity and line intensity map is the sum of all halo intensities in a particular direction.
That's right. Yeah. Well, in a particular direction at that frequency that's emitting at a particular frequency, because the halo intensity, remember the line intensity map, you have a map at each individual frequency, okay. And so you can think of the whole qubit. Yeah.
So your line intensity map is spectral line,
yes,
not line of sight.
Yes.
Okay.
That's right. Okay. So what's normally used in order to construct models for line intensity mapping are what's known as empirical models. Empirical model can be defined in different ways depending on the field you're talking about. The way I'm going to define it in this talk is it's an extrapolated model of emission constructed from correlations seen in data or simulation. So you take some data or simulation that says, okay, I have this quantity of line of like a luminosity in a particular, or flux in a particular line, or intensity in a particular line, versus versus some property, like, and that property could be the metallicity, the metallicity of a galaxy, or the star formation rate, which is the amount of in a galaxy, or the stellar mass of a galaxy, the total amount of mass in stars in that galaxy. And so you can make certain models. You can use those correlations in order to make sort of a simple prediction of how those two quantities are related. Okay. This is most widely used in line intensity mapping modeling. It's used because they're easy to make and they're very easily inferable. You can then, if you have a relation like this, you can then invert it in order to say, well, if I measure some intensity in a particular line over a large area, I can use that to then invert it to make a prediction for how much star formation there is, so how much stellar mass there is per galaxy. However, the thing is that these models are very limited in their applicability. For one, you have to use them, you have to extrapolate them way beyond when they're observed. Either you have to extrapolate them to pass the property values that you assume that were actually used to create that empirical model, or you have to apply it to epochs that were in which was not, like, you might measure this, you might use data from the local universe and then extrapolate that to earlier times or higher redshifts. And so that's a problem that can lead you astray. One thing you'll notice, I see in this plot here, is that you see this is a plot. These are some empirical models of CO carbon monoxide luminosity versus halo mass. And one thing you see is that in this region where basically most of the galaxies that we use live, you see they all predicting pretty much the same value for the luminosity. Whereas if you go far away on the other side, you try to extrapolate away from that, you get much higher discrepancies in the different predictions. Also, too, one problem with these models is that they don't directly model multi-line luminosity scattering. So the idea is that if you have two lines, they're not necessarily, those lines are going to be random, because in reality they're going to be produced by the same. If you're looking at one galaxy that produces two lines, though the processes that relate two lines could be very correlated based on based on the properties of that galaxy. But the empirical models typically don't account for this. Like, they just treat each line independently. Also, to a related issue with this is that you don't necessarily get self-consistent predictions. In reality, these models will, in reality, these line emissions, if you're trying to assign a line for a particular galaxy and you're trying to make a simulation, for example, you may try to put some scatter on that line, but that's not going to, if you don't know the correlations between those lines, which can depend on the galaxy itself, you're not going to be able to model it properly. And so that could bias your predictions when you try to use either the model directly or try to use it on a simulation and then compare the data. It can cause problems. So an alternative is to use hydrodynamic simulation. So you can hydrodynamic simulation is when, well, there are in-body simulations where you just take dark matter only simulations where you have like macro particles of dark matter, and you just allow them to be influenced by gravity. Hydrodynamic simulations taking it a step further, where you use gas particles. You have to have some rule for how gas baryons interact, and then you allow that to make a simulation. Obviously, it's much more complicated than that. You have to, usually you have way too many particles, and it's hard to do. There are very intelligent ways to sort of simulate certain regions that are important and not so much the other regions that are more dilute. But that's basically how these line intensity mapping simulations, how hydrodynamic simulations can work. And then if they predict line emission signals, you can then use that to create a simulated line intensity map. So this is sort of the gold standard for predicting what the emission signal should be for a line intensity map. However, these hydrodynamic simulations, they still lack the resolution to be able to simulate basically in its physics of the interstellar medium. And so you do have to create what are known as subgrid models, where you make some kind of rule that then describes, given some conditions, what the interaction should be. In addition, these simulations are very expensive to run. Sometimes they can come out as much as once a year, particularly for less simulation with the snapshot shown here. And so you can, and so these can be very expensive to run. And so you're not going to get, and so normally you want to run a lot of simulations in order to have best statistics when making predictions based on simulation. And also too, these things can be difficult, these simulations can be difficult to interpret because the interactions that take place here are so complex. It's hard to come up, it's difficult to come up necessarily with rules that you can make that will be interpretable in order to then, in order to then, actually use them for inference later to do something. So an alternative, which we've been working on, is a method called semi-analytic modeling. In semi-analytic modeling, or SAMs, we actually use an in-body simulation and paint a lot, and basically we determine rules for star formation and galaxy evolution in order to create simulations of galaxy evolution. Now, in one sense, what we're doing is we're basically saying full hydrodynamic simulations are too expensive. So what we instead do is we create rules that we can use in order to make mini simulations of large scale structure and including the galaxy physics. These are better than empirical models because the rules aren't just some general extrapolation. What we actually use is we calibrate this to hydrodynamic simulations and observations, and we have rules that actually govern the physics of gas within galaxies, well, of the gas within galaxies and throughout the halo, in order to then account for nonlinear effects like stellar feedback, the ionization of the gas within galaxies, as well as gas heating. And so this will allow us to actually create more realistic predictions for how galaxies evolve. So here at the bottom here is sort of a flow chart for how this is constructed. Whereas you start off with the dark matter halos from an in-body simulation, you then have, based on a simulatic model, you then decide how many galaxies and what their proper and what galaxies will orbit that would live in that halo. You then have the simulating model also then predicts what the dynamics of the gas within those galaxies would be, including how stars are formed, how those stars then cause feedback and emit UV in order to then affect the surrounding gas. And then, so this is what the main SAM does. And then there's an actual add-on that then says, given the properties of the gas in the galaxy, what's the emission of different lines should be. And so then that's this extra piece which we saw called the sub-millimeter SAM. This is what actually determines what the emissions of galaxies and what the emissions of galaxies would be, which we can then use to actually make simulations. This is an example of the kind of calibration work that has to be done though with the SAM, where you basically take some measurements, use some measurements of luminosity and the star formation rate, and then with the SAM, you can then predict. It then predicts what the relation should be at lower rates. Now, at lower star formation rates. Now, the thing is that one thing to be mindful of is that we don't believe the SAM. Okay, we don't trust the SAM. We're not saying that the SAM is truth and that this is our predictions and that we don't have to test it and we can base all our measurements on the SAM. But the thing is, what we want to do is you want to use the SAM as a prediction, just like any other prediction. It's more intelligent than the empirical model, and it's much less expensive than running a hydrodynamic simulation. So it's better. So that what's useful of it is that it has the potential to be better for inference. And so the hope is that with data from line intensity mapping surveys, as well as galaxy surveys and in the sub-millimeter, we can then test this same model. And then if it makes predictions that are incorrect, we can always, we can adjust the model in order to better match simulations, but we will learn something. But the point is we will learn something by doing those tests. And the semi-analytic model, I feel has great potential in order to be able to do those tests. So there's some work that we've done. Some former student Chungshi, she used the SAM in order to make simulations for line intensity maps. This is simulations of C2, as well as what we designated as interlopers, carbon monoxide, as well as neutral carbon. We also made simulations of the cosmic infrared background, which at that time I'll mention more about that later, coming from young dust and stars. And then also too, we also used the SAM itself to then make empirical models as well, empirical models relating the luminosity of a halo to its mass. And so here is just a sample of some empirical models we were able to construct for immediate lines in the microwave and infrared. However, it's still interpreting is challenging. As I mentioned before, it's hard to interpret with empirical models, even empirical models that we made. Well, this is some work that Patrick did, where he showed that if you try to interpret CO as a tracer for molecular hydrogen, which is molecular hydrogen is important because it is a constituent that is a chemical constituent that you need for star formation. Many times, and so you can actually come to wrong conclusions. So earlier I showed a measurement of molecular hydrogen using the CO map. So Patrick took basically that interpretation and considered, well, what if the SAM was actually the truth? And what he found, and compared to other models of what we call alpha CO, which is a ratio predicted between molecular hydrogen mass and CO luminosity. And what you find is that what he found was that based on which model you use, you can get a very different measurement of what the molecular hydrogen density is. And so this just shows that basically you're sort of playing a dangerous game with empirical models. I mean, we still use them, as you'll see later when I talk about EXCLAIM. That's what we have now, but what we want to do, and so they're still useful as tracers, but one thing we want to work on is, are there better ways to do this analysis? That is
Sorry, Anthony.
Yes.
I'm totally lost. So if I take some big fat nearby galaxy, I can measure it to depth, right? I know everything, all these lines, everything.
Mhm.
But apparently, and then why do I need some semi-analytic model or something?
Because you can measure the lines, but we don't just want to know what the intensity, we don't just want to know what the spectrum of a galaxy is. We want to know its properties. Right, the lines are only good as far as they can tell us the conditions of that galaxy. And and particularly you want to do it over a large population so we can learn something new about how galaxies work, as well as
But you compare your models to the actual concrete galaxies, don't you?
Well, yeah, that's part of it. So the SAM itself was also calibrated using both simulations and as well as data. And then as we get new types of data, we can further test these models in order to learn, and we can further test these models. So and so now it's a challenging game because, well, are you testing the model or learning something about the galaxies, right? Because if the model is off, then you learn something about the galaxy. So one thing you want to do is you want to have multiple observations using the same model, and then if there's inconsistencies, then that can tease out that something is wrong. But if all the different statistics then agree and they all fit with data, then that gives you more confidence that the model is actually correct, and then you can use that in order to learn about how galaxies form and be able to model them correctly. So it's a framework that I've worked on developing over the past couple of years, and which is the idea of, well, what do we actually want to measure as far as galaxy properties in order to learn more about galaxy physics? What do we actually want to measure? Well, what we really want to measure is, well, we know that line intensity mapping is not really a probe of an individual galaxy, but it's really more of a population probe. You want to probe the general properties of the full galaxy population. And so one way, and you can sort of model that, is you can say, well, if you have, you can sort of describe it as a distribution. You can say, well, if I have a certain set of galaxies, they're, if you take a distribution of their star formation rates, they will have some, you can take a histogram of that and they'll have some distribution. If I want to say, well, what are their distributions of metallicities, for example, I could, make a histogram of that and have some distribution. And ultimately, like the full distribution, if you consider multiple properties, is going to be a multi-dimensional distribution, right? And so one thing that we developed using the SAM is that we consider, well, there are actually five properties that really govern how the galaxies are the same. Now, this may not be true in actual physics, but for this model, it's these five properties that influence it. Those properties are for the emission of for a galaxy would be its molecular hydrogen mass, its star formation rate, its stellar mass, it's the size of the size of the disk, as well as the metallicity, which metallicity is basically the fraction of matter that's not in the form of hydrogen. And so what we can do is we can say, if we knew what this distribution was, and we knew what the luminosity of a galaxy would be given these set of five numbers, then we can construct a model for what the luminosity of a halo would be. Because again, remember, the luminosity of a halo is just the sum of all the luminosities of the individual galaxies associated with that halo. And that number of galaxies will be given by this distribution. So we treat this not as a normalized distribution, but an unnormalized distribution where over all galaxies, it would integrate basically to the number of galaxies, then this formula would give you what the luminosity of a halo mass is, of a halo is, where the luminosity of a halo is given by this distribution times the luminosity of a per galaxy integrated over all five properties. And so why is this important? This is a neat trick, but what's important is that this number on the left can be used directly to predict what the intensity on the sky would be. And so the key thing is that if we can measure intensities on the sky, then we can use that as a way to probe. And if we knew what this luminosity relation is given galaxy properties, we could then measure this phi here with this distribution. Now, of course, it's unrealistic to take one measurement and do this. But if you have, the point is that if you have measurements from many lines and many statistics, they will all vary based on what this luminosity is. But if this is something that we know, they will all those statistics will be sourced by the same distribution of properties. And so the key thing is that if you do multiple measurements, it's conceivable that you could potentially measure this distribution.
Why is this distribution the same for all lines?
So this distribution is independent of the lines. This is just the galaxies. So the point is that all the galaxies will emit the same galaxy population produces all the emission. And so in particular emission in different lines. And so if you can measure the intensity, not just the intensities, but all the statistics like that I mentioned before, you can get much data that you can use together. You potentially use you would have much data that you could potentially use to constrain this distribution.
So you assume that the same physical properties of the galaxy will control any spectral lines.
Yes, I'm assuming that it's that for each individual galaxy, it has a certain set of properties, and that's unique, and those properties will determine the full spectrum of emission for that galaxy. Yeah. So anyways, okay. So this is work that my former student Yucheng Zhang, who's now a postdoc in China, this is where he's been working on. So here's an example of what this distribution could look like in our five properties. Where this is just a picture of it's a picture at one redshift over a halo mass range of 10 to the 11, well, over a small mass range But we actually simulate this for many redshifts between redshift 0 and 10 for the mass range and 10 to the 10 to 10 to the 13 solar masses, which is the mass range that matters the most for line intensity maps. And we basically do this over a million bins, including bins that vary over mass, as well as a million halos separated into 1,000 mass bins. And what we find is actually one thing we wanted to test was, well, we could obviously just measure this using the SAM, but can we actually model this? Can we actually make a model that retains the information of this? And what we find is that by using a Gaussian mixture model, having a two-component Gaussian mixture model, so that's like just two Gaussians added together, that models the multivariate covariance of this, actually is enough to predict observable quantities within 10%, which sounds bad for normally in cosmology, but that's actually really, really good for galaxy evolution compared to other models of galaxy evolution. So here's some things that we found. So this is the plot of the star formation rate density. As you see, the blue line is the data, and on top of that, you can barely tell the difference is one component Gaussian mixture model, that's GMM1, and two components in GMM2. And see in the bottom here shows, well, I should put it on the screen. The bottom here shows what the difference is from what the SAM directly predicts to what is predicted by what is found by these Gaussian mixture models. And this is important because if we want to, the reason why we want to model this Gaussian mixture models is because if we want to infer this, we're not going to infer directly on the SAM. We need some model in order to do inference. And so by showing that the Gaussian mixture model can retain a lot of the information, that's hopeful that we could potentially make a measurement with this in the future.
Okay, so when you say data, it's actually data. Someone's measured the star formation rate as a function of redshift.
Well, you mean for this in particular?
Yeah, what is the data?
This is all model. This is all model. There's no data here.
Okay.
But then what this is saying is that what we did was we took the SAM, that's the blue line, and then we said the SAM predicts the blue line, but then we took the SAM and then we measured this. We measured the distribution, and then we modeled the distribution using a Gaussian mixture model. Okay. And then by that, and that's an analytic model. That's something you can actually write down on paper. And so the point is that actually does really well in getting the full information. I mean, it doesn't get all the information, but it does pretty well. And so we could, in an inference in the future, if we have good data, we could actually use this. We could actually use those Gaussian mixture models to be able to sample the covariance, for example, that would represent this distribution. Okay. One thing we also looked at was how this. So obviously, we only considered this using the SAM. We also did a comparison with this determined from a hydrodynamic simulation, illustrious T and G. And so we did that, and as you see, there are discrepancies. That is a good thing. It's a good thing that there are discrepancies because you didn't believe the SAM anyway. The point of this is to say that, but we don't really fully believe illustrious either. So the point of this is to say, you see, there's a difference. There's a difference that is distinct between these two. And so what you could do eventually is you could implement this in a measurement where you would have a prior that would represent sort of the spread of different predictions. And then the hope is that if you do this with a measurement, you would get more information than would just be in the prior, such that you could actually learn something about this distribution in reality.
Are you saying that if the observations look like one of these models, you would be able to rule out the other model?
Yeah, well, we haven't analyzed that. So in future work,
I mean,
want to do more
infinite
work.
signal noise observation.
Yeah. Yeah. Okay. And work that there's work. I would say one work that Patrick is working on now. So this will be published soon, and then Patrick is working on work that actually shows that for this luminosity model related to galaxy properties, he was able to show. So that's this here. He was able to show that using Gaussian processes, he can model this. If you use the SAM in order to construct the model, he can actually get, you can actually make an empirical model that's accurate to within 1%. So that is hopeful that we could actually be, because you would really want to be able to know that function in order to do this type of inference. And so it's hopeful that we could do something like this. And what we plan, and one thing we plan on doing in the future is to actually apply this to data, to Pathfinder data eventually, and in preparation for doing it on in the next generation of servers. So I will use the rest of my few minutes to discuss EXCLAIM. So EXCLAIM, it stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. It was designed as a collaboration of 8 institutions, which includes more than 40 members, including NYU, of course, with PI being Eric Switzer at Goddard Space Flight Center in Maryland. And it's designed to answer some important questions, like, for example, what led to the dramatic decline of star formation at redshifts less than 2, which is, and then what are the typical abundances and excitation of molecular gas which form stars? How do those occur? What is the abundance of molecular hydrogen in the universe as well as in the Milky Way galaxy? And also as a pathfinder to eventually inform how we design future surveys that would be more sensitive and cover larger areas so that you can eventually do cosmology. So in order to do a first detection, anytime you want to do a first detection with maps, you want to use a cross correlation because you want to be confident that you're not seeing noise or foregrounds. And so what we do is we're going to cross correlate maps created by EXCLAIM, which is a balloon survey flying at 36 kilometers above sea level. And we're going to cross correlate these maps with quasars from the Sloan Sky Survey, and then it's going to be over a range of 420 to 540 gigahertz. And so this should access to both linear and nonlinear scales. This will fly out of Fort Sumner, which is in New Mexico. The first engineering flight right now is scheduled for fall of 2023, so that's next year, with an engineering flight which will contain 1 spectrograph. Then the full flight the following year hopefully will contain 6 spectrographs. So one thing that our group, in collaboration with the rest of the team at
So what do you call detection? What are you detecting?
So we're going to begin it. First we're going to make maps, and then we're going to use those to construct statistics, specifically the power spectrum, as what I mentioned earlier, as well as a histogram of intensities, which we call a voxel intensity distribution. And we're going to use those statistics. So first we're going to detect the statistics, and even just detecting those will be good because it'll say, okay, there's something there and it's correlated with large scale structure. So
So you will detect correlations as a function of angle or something.
Yeah. So first we'll detect that, that's what's pictured here is basically this column here represents our models of what we think the signal will look like from ionized carbon, as well as one of the CO lines. And then this column here represents what we think the sensitivity we think we'll be able to reach using these instruments. And so with these dots represent different models predicted by different astronomers. And then these bars represent the precision that we'd be able to measure this thing. Now, what this thing is, this A here, this represents the ratio between the actual power spectrum we'll measure versus a fiducial model. So all these are scaled with a fiducial model. This is the trick that's used a lot in first detections as well. Like for example, with CMB lensing, this was used in many other quantities in cosmology. This was used as a sort of first detection. So it's a way in which you can quantify a detection of correlations with large scale structure. And so what this shows is that for both C2 and CO, we should be able to discriminate between different models in the literature. And so this will get us on the path to be able to learn more about these galaxies, but more important, be able to learn what the emissions of these galaxies are, and then more importantly, maybe even learn something about it. For CO, this is sort of the limit. This is the most you can do just because the intensity is just not high enough to be able to do more than this. For C2 though, we do have the potential to be able to do some science specifically to measure the star formation rate density. So here, if we can measure the this voxel intensity distribution in the power spectrum, you can constrain the C2. You should be able to. These are some forecasted constraints. This is not real. This is what we predict we could be able to do with EXCLAIM to measure parameters of the relation between C2 luminosity and halo mass. We could be able to measure the intensity of C2 and it would be able to discriminate between different models. And depending on the model of how luminosity is related to the star formation rate, we should be able to we could potentially detect measure the star formation rate density. And this is what the orange cross represents what we would be able to measure, within the vertical being the uncertainty compared to other predictions that already exist just using galaxy surveys. And one thing you see here is that this would be competitive with those predictions, and it would and then it has an additional advantage in that this is a global measurement, which should be properly weighted with all the galaxies that exists in the cosmic volume versus these other ones, which are just measurements from small samples of galaxies. And so this is a more.
What's that redshift at?
So this is that redshift 2.7 specifically.
Okay.
And this beautiful formula with power 1.79.
Yeah.
Summary of the curve on the right.
So this is one model specifically from this paper. We're not actually that confident in it, and so one thing we're working on is how to make more accurate models. It shouldn't affect this much, but as far as predicting an uncertainty, but when we actually do the measurement, we will need to have a confident.
But this comes from the model. It does not come from just drawing this blue line.
The blue line, sorry, which.
On the.
Oh, right, yeah. So the blue line comes from this is a fitting function from Baruzzi, from Peter Baruzzi, who's been actually sort of one of the main experts in measuring star formation, and this is from this is from this fitting function that he has. That's the blue line is. That's not based on anything with EXCLAIM. That makes sense. Did I answer your question?
Yeah, but
Okay.
I'm still charmed by this beautiful formula.
You don't have to believe it. I should say, one thing that my group is working on is trying to use the SAM to make more realistic models in this, because this is scaled again off of one intensity measurement. Actually mine, but you'd want to use a better model. So we're actually and one of my students is actually trying to, and Allison, another student, they actually on separate projects sort of working on ways to improve these relations and make more.
Probably your better model will not be so beautiful.
Maybe it won't. It probably won't look this nice, but we'll see.
That's for sure.
There are many beautiful rational numbers that that's what it could be.
Yeah, I mean, God didn't get 1.79 hours. Okay, so I think I'm running out of time. So I will just say future plans. So I sort of mentioned some future plans in developing better models. One thing we want to also do is we want to be able to make faster simulations. So one thing that one of my students at Colloquium is working on is seeing if we do use empirical models on an in-body simulation, how much are we missing versus using the full semi-analytic model? Because semi-analytic model is much faster than hydrodynamic simulation, but it's not as fast as you could use an empirical model. So one question we might want to ask is, well, can we make even more simulations even faster just using empirical models? And if we do that, what information are we missing? And so that's something that he's working on and my group is working on. Then also one thing that will come up is as EXCLAIM data comes in, we will perform that analysis. I will lead that analysis with collaborators, both people here, my research group here, as well as collaborators at other institutions. And so that will be performed. And then one thing we'll also look at is cross-correlating with DESI galaxies as well as the DESI data sample increases to cover its full mission. we could potentially use those galaxies as well as a cross correlation source. And then one thing, and then of course, as I mentioned before, with this conditional galaxy property distribution that we want to measure, we want to be able to simulate it. We want to be able to do a measurement. First, we want to be particularly with EXCLAIM, but of course we don't expect that EXCLAIM will be enough. The data will be sensitive enough to really be able to measure it. So one thing we want to look at is what to be able to simulate how this work in future data sets. Could we actually constrain this distribution, or can we learn from it in order to then be able to prepare for particularly prepare for much better data sets? And this will include not just line intensity mapping, but also galaxy surveys and as well. And these could be applied, and these methods could potentially be applied to SPHEREX, which is the NASA-funded survey that's going to launch in 2020, the space mission that's going to launch in 2024. That has one part of the component being a line intensity mapping measurement of Lyman alpha and H alpha, and as well as PIXI, which is not funded, it's perennially being proposed. I recently joined the collaboration in order to model line intensity mapping for that survey. If that were to work, that would really blow these surveys out of the water, at least in the microwave regime, and that would launch. That would be more in the 2030s. That would happen if it does. So I think I'm out of time, so I'm not gonna be able to talk about cosmology, but you can ask me about it later, and I'll put it in my summary slide, and I'm happy to answer any questions.
Right, so I don't think I understood much, but can I summarize it and you will tell me if my understanding has anything to do with reality?
Okay.
So you will run a CMB-like experiment, but at slightly different frequencies, and the signal will be dominated by line emission from galaxies rather than by relic radiation.
Yes, I mean we can. Yes, and pretty much. I mean, the signal, the signals will still be there, but we can treat them well to remove.
And that will allow you to know some gastrophysics of galaxies. You are not claiming to be competitive with CMB people in terms of cosmology, at least not yet.
Not yet, and not with this survey. With future surveys, though, the hope is that as technology develops, one thing that will be improved is that we'll be able to pack more detectors per area on and so that would allow us to increase our sensitivity. And then as we expand to a larger range of frequencies, we could survey more lines over more volumes in cosmology, and in particular, and then you eventually will win because the CMB is only one plane, it's only 2D, whereas this is 3D, and so just by being a 3D survey, you just access more modes.
Isn't that similar to this 21 centimeter? They have been promising to measure non-Gaussianity to Multasevich.
Yes.
level.
So there are advantages and disadvantages. The advantage of 21 centimeter is that it's long wavelength, so large field of view, which means you can map larger areas much faster than some of the surveys I'm talking about. So that's what's good. The bad thing is, of course, that you have all this radio contamination that you have to worry about, and also too, calibration is hard as well. So that's what the problem is. However, they've gotten good results by cross-correlating their maps with galaxies. So that's helpful at low redshifts, and they've been getting better at removing the foregrounds, such that eventually they'll probably make it there to be able to be to at least do some of the promise. I mean, now guys. I mean, some of these things are still hard, so we'll be able to. I don't doubt they'll be able to get all the everything, but no experiment every well, part of a physics is a different story, but at least in most astrophysics experiment surveys, you never get everything you want. But now for the lines we're looking at, they're smaller wavelengths, so you can't map the sky as fast. And so that's its disadvantage as far as getting large volumes like 21 centimeter can. But the advantage is that the foregrounds are much lower and well behaved than 21 centimeters. So that's the advantage of lines like CO, C2, and H alpha, some of the emission lines. Smart.
So I just want to make sure I squeeze the juice out of your talk or understood as much as I can.
Yeah.
So what your group has done is you've made some software, some packages, so they can connect some inputs of like features of galaxies, some parameters of galaxies to observables.
Yeah, so that's what we've been creating.
And the advantage compared to existing stuff is that it runs faster, so you can run more simulations.
It runs faster, so we can run more simulations, and that's something we're going to be. That's not something we've done yet, but it's in the pipeline. And yeah, it's more realistic than the empirical models that is being used, and that even I am currently using for EXCLAIM. This will be better. This will give us more information.
And so, like then in the bigger picture, like what will we understand by using this that we don't know now? Like,
so we will get, so what we will do now with empirical models is you'll be able to get.
like, sorry, I mean,
You'll
it's
be able
super
to-
basic. Like, I don't understand like what these galaxy parameters that go in tell you about the world.
So the parameters themselves don't tell you about physics themselves. They'll be a distribution. The thing is that physics models of galaxy evolution will predict what those distributions should be. And so you would want to use, and so it just brings you a step closer to being able to relate, observations to physics. Like to go from physics directly to the emission lines, you need that step in between to model galaxies themselves. And so this gets you a step closer to be able to learn more about the physics of galaxies.
So like, how do models of galaxy evolution differ from each other? Like,
So different assumptions, they're made with the different assumptions, how you say, if a gas is heated by UV, how does it heat up? How does it expand? Like even those, what do you need in order to create a star? What conditions you need? Like all those things can differ between different simulations.
and so like if one model is right, another model is wrong. Is that like a niche thing where it's like, okay, the astrophysicists really care about how this galaxy formed, but in general doesn't, or like, does the fact that galaxies formed, these models disagree, like have some fundamental implication on like the way the universe exists?
Well, it determines the way that the galaxies exist, and it could influence. Potentially, you could try to extract. If you're confident in the model, you can then say, well, what would it be like in the future? Like, what star formation would look like, billion years, yeah, and then so I think I lost my train of thought, but hopefully also.
I mean, it's sort of related, but these C2 predictions, like all these different lines from the different models, why are they so different?
Because different, so.
Yeah.
Okay,
each of those
look at
dots is
individual
like-
ones.
Each of those little dots is like a different model from a different. Like,
Yeah, so
why do they vary by like a factor of 100?
So we don't really have good measurements yet. So one thing is some of these are based off of simulations. Some of these are based off of different, and then one important thing is, right, it goes back to this picture here, right? You can do a measurement with galaxies, and if they're all clustered around these mass halos, then you don't predict the same thing. But when you extrapolate out, which all these models do, then you get difference. And then the problem is that the intensity signal doesn't just depend on what happens here; it depends on this whole range.
So they're like constrained your 10 to the 12, but the way they extrapolate into like regimes where you can't tie them down is different. Okay.
Yeah, but but line intensity mapping should give more information across the whole mass range that should constrain.
So we have a lot of questions, so let's thank Anthony again. And then